Okay, this session, let's pull everything together by applying it to a particular paper. So I hope you've had a go at this paper here. Now, the first section is about Popper, so we'll go through that. And the first question is, concisely state the theory that the authors present as being put up to test. So, in terms of what we've been discussing before, this is asking for the substantial theory, right? It's asking you to isolate what substantial theory was presented in the paper. So the substantial theory is hopefully bold, interesting idea that's falsifiable and, in fact, is something that would be given up if the if everything about the experiment works well and you get certain results. So when you think about a substantial theory, one thing to think about is, can you make it as bold and interesting as possible? So, to take a different example, you might be reading a paper about priming, if you prime people with words like, I don't know, achieve, win, words like this, will they work hard on crosswords afterwards? So you might say the substantial theory is priming with achievement words makes people work harder on crosswords. Okay, maybe. That is a claim that a particular experiment might be putting up to test, that they would give up if they got certain results. But there might be a bolder way of putting it. For example, priming people with the concept of achievement makes them work harder on tasks. And you see, you would give up this second theory with the results of the experiment. So that's an even bolder claim that is being put up to test. So when you try and identify substantial theory, try and think about what's the boldest, most interesting claim that I could state here. Does that make sense? Because what we're interested in as scientists is bold and interesting theories, not just any old theory. And that goes back to in my lecture when I was saying the goal isn't to keep as close to the data as possible. The goal on a Popperian view of science is to have interesting ideas that we test. And I subscribe to that personally myself. So those are just some thoughts in terms of generally tackling this task, and indeed thinking about your project or any research you're involved with. But now, this particular paper. Just have a go, first of all, saying to the person next to you what you think the substantial theory was being put up to test in this paper. Okay, so this is what I put down here. Actually, I've taken it pretty much from the paper. So I think in this case, it's not terribly problematic, although maybe you disagree. People who view apologies as socially desirable following interpersonal transgressions will overestimate the value of an apology when receiving it in imagination compared to when they actually receive it. And then for study 2, hence people believe they'll be more trusting after receiving an apology than they really would be. So I think those are the ideas being put up to test. Those are the substantial theories. Any comments on that? Does that seem reasonable? Yes?
So maybe we could just try to make it bolder, like people tend to overestimate everything that they imagine that they would receive rather than they actually receive, rather than just for the apologies.
Yes.
So maybe, is that still sensible?
Yes, so there is an even bolder hypothesis that in every case in which you, how should we put it, that you imagine a social situation or an emotional reaction to a social situation.
Rather than just apologies.
Yes. All right. Yeah, good thought. So let's yes, that would be a bolder one. Okay, so now what pattern of results, if any, would falsify the theory? Yes, sorry.
Just what this person said is really interesting, because when I was reading the paper,
Yes,
I looked up David Cramer, and he's interested in forecasting errors, right?
yes,
So there's, on the one hand, the paper could be about another example of forecasting error.
yes,
Or on the other hand, it could be about apologies.
yes,
So it seemed like if you didn't know what the author was actually interested in their career,
yes,
or what they call the research program, I think, from the Lakatos thing,
yes, exactly.
then it would be ambiguous what the boldest hypothesis.
What the boldest could be. And so there is an issue here, to go back to, for the sake of recording here. So the bolder hypothesis is that forecasting errors in general will overestimate. And as a general claim, that would be falsified by not being true in this case. But there is an issue: do we want to treat that as falsifiable, or do we want to protect it as a hard core? So we'll come back to that issue when we consider Lakatos, because we might regard the bolder theory as true in many occasions, but not necessarily always. But we'll still use it as inspiration in our research. So then we move into Lakatos territory. Yes, very good point.
Just briefly, if we can find a bold but kind of brief way of putting it,
Yes.
is that acceptable? I see your example is quite a long sentence, but if we can kind of condense it.
Yes, you could condense it. I was covering studies 1 and 2. You might have concentrated on one of those studies more than the others, so you might have just done half of that, or you might have found a way of putting it more briefly to cover both. That would be absolutely fine. Yes. All right, so now what would falsify this claim, or the claim that you've used? Because if you use a slightly different claim, as we've been talking about, there's not necessarily a right answer here, and it might be in a given paper, the authors don't clearly state a substantial theory, but you read behind the lines and get one, or you come up with a different one than the authors have, and so on. So it's not as if there's you must say this. There's a range of answers that you could give. But once you've decided on the substantial theory, that then sort of determines or influences what answers you can give for the following questions. For example, what would falsify? Or what are the auxiliary hypotheses? We'll come to that. So for the substantial theory that you've given, what would falsify it? Just have a chat with the person next to you. So for your substantial theory, it might have been a bit different. What results would falsify it from this paper? Okay, so the theory would be falsified if people rated the apology or experiment 2 rated the apology as more valuable or gave more money in reality than in imagination. Okay, so if it went significantly in the wrong direction. So the little trap, as it were, or the thing to watch out for, is that a non-significant result in itself would count for nothing. Okay. So a non-significant result would not count against the theory, not in itself. Okay. So that's the little thing to watch out for, because the whole literature behaves otherwise. So then, but we do have means for interpreting what would be non-significant results in meaningful ways. So you could have a Bayes factor less than a third. That means you would have evidence for the null hypothesis and against the theory. So that would count against the theory. Or if you're able to come up with a minimal meaningful amount that you're happy with, and the confidence interval did not exceed that minimal meaningful amount, then that would also count against the theory. So we're going to look at these, what is involved in A and B here, as we go through the assignment. Yes?
Would it not be falsified if they found that people were more accurate at predicting how much the opportunities? Would that be an answer?
Yeah, so that in effect is a non-significant result. Right. Yes.
They didn't measure accuracy, they just inferred it from comparing how they experience, how they imagine mythology and how they experience it.
Yeah, so accuracy amounts to no difference between imagination and reality.
So that wouldn't disprove that wouldn't go against the theory.
A non-significant result wouldn't, and the reason is because you cannot infer from a non-significant result that imagination and reality were the same. That's the problem. So if you found that they were the same in the population, yes, that falsifies the theory. The problem is, how do we get evidence for that in the population? And a non-significant result is not evidence for sameness. So how do we get evidence for sameness? Well, a Bayes factor. Or, if we can have a minimal, meaningful amount, so we say it's same as long as it's not, as long as it's only trivially different, then we can use intervals. Right, so the next question is, what background knowledge inspired this theory that is not being directly tested? So we have the substantial theory, and that theory might have been inspired by a number of things, but it's not actually being put up for test. So not all theories that will be mentioned and findings that are mentioned by the authors are actually being tested, but they're relevant for why they postulated this substantial theory in the first place. So just now have a little go with your partner saying what you thought about the answer to that question. Okay, so a point just came up about the previous slide here is I've sort of constructed half of a null region, right? I didn't do a full null region. That's because it doesn't matter how far the confidence interval extends in this direction. We still falsify the theory because it's directional. Yeah. So that was, I think, an interesting point just raised. Okay, so now let's look at some theories or findings that help motivate the research but aren't being directly tested. And was a point brought up earlier, people's poor effective and behavioural forecasting in other domains are discussed. So in terms of the, this is why I say it depends on what your substantial theory is. So in terms of the substantial theory being about apologies, then whether the same issues apply to how sad you'll be, how happy you'll be, and so on. Well, maybe it applies to some of those domains and not others, who knows, but it could still apply to apologies. So the status of that research, we don't need to assume it's safe, you see. Yes, it did inspire the substantial theory, but the experiment has an integrity all of its own that depends mostly on this half of the diagram here. So whether behavioural forecasting applies to sadness or not, well, it doesn't matter. We can still test and have integrity in this experiment as a test of its application to apologies. That's why it's good to separate out the role of these different theories. And part of this comes down to Popper's philosophy that we didn't induce the substantial theory from anything. There is no method by which we can infer this theory and say, therefore, it's right. What we do is we guess it, conjecture it, and then we test it. And whatever we use to inspire ourselves to say it, that's great. But once we have the theory on the table, that's what's important. And then whether we've got the right conditions to test it, which is this side of the diagram. Now, what background... So now we're going to have a look at that side of the diagram a little bit more closely. What background knowledge must be assumed for the test to be a test of the theory in one? So we have here auxiliary hypotheses. Why don't you just have a go to define to the person next to you what an auxiliary hypothesis is? Okay, so you could define auxiliary hypotheses as the things you need to assume to go from the substantial theory to specific predictions. Okay, so what connects the substantial theory to the predictions? The substantial theory will talk about what you're interested in, like the extent to which people value an apology. But in the end, what you need is a particular dependent variable. You need a measure of value, right? So maybe you get people to rate how much they value the apology. Or you see how much money they give. or you could do something else. But what you have is a measure. And there's always the question, does your dependent variable measure what you says it measures? And so there's an assumption there, maybe an assumption that needs to be tested further. But at least you need to wonder, do your variables measure what they say they measure? When you manipulate something, have you manipulated what you think you've manipulated? So there'll be all sorts of assumptions, because a substantial theory is ideally something fairly general and interesting, which you could test in different ways. And you somehow have to go from that generality to the specifics of your particular experiment. And we'll see examples of that. So one way of looking at this is that you make a prediction, and then there's some possible falsifying observation. Let's say you do get the falsifying case. Will this discrepancy here be transmitted back to the substantial theory, and you say that counts against the substantial theory? Or if you're feeling particularly robust, that falsifies the substantial theory. You see, instead of a discrepancy in the predictions being transmitted to this substantial theory, you might give up some other assumption. You might say, oh yeah, that's because we just use this rating scale of how much they value the apology. What does that mean? I don't think we measured how much they valued the apology very well. We need to measure it better. So then the possible falsification stops here, you see. So what we need to do is to make sure the assumptions we make in deriving predictions are just safe enough that we would give up the theory rather than those assumptions. So does a falsification or an unpredicted outcome transmit back to the substantial theory? That's the crucial question. Because if it does, we're in business. We have a falsifiable theory potentially being put up for falsification, and you would give it up if you had certain outcomes. Now, in terms of it being a severe test, certainly we need that, because for a severe test, we do need the predictions to follow clearly, firmly from the theory. So the predictions follow from the theory. The predicted outcome is likely given the theory, if the theory is true. We need that for a severe test. But we need something else for a severe test. Let's say there's another theory out here, and this is where this side can play some role in the scientific nature of what we're doing. Let's say some theory out here, like, use example, demand characteristics, because it comes up so often. Subjects suss out the experiment and try and give you what you want. Maybe some theory out here would produce the same outcome as your theory. Now, still true that a falsification will transmit back to your theory. So we're still in the business of science. But there's another problem. Let's say you get a supporting result. The prediction is a success. Does the credit transmit back to the theory? Well, if there's another theory that predicts it, it's not obvious that this result strongly corroborates this theory here, right? Because there's something else that's predicting it. Or in terms of notion of test severity, even if the theory were false, you might still get the same outcome, say because of demand characteristics. So it's not a severe test. The theory hasn't been made to stick its neck out. Right? That's what we want severe tests. You say, if it's going to be falsified in any situation, surely it's here. I've got a feeling it's going to fail. And then if it passes, you say, that theory is strongly corroborated. So that's what we're looking for a severe test. So what background knowledge, in other words, auxiliary hypotheses, must we assume for the test to be a test of the substantial theory? We're talking about the auxiliaries here and other theories that might predict the same outcome. So just have a go at talking about that with the person next to you, and then I'll come back. All right. So now I'll go through some, and by the way, it's not as if there's a fixed number of these, or that you have to mention a fixed number. there's always, you can go on forever with the things you must assume, so just like you have to assume the statistical analyses were appropriate, the distributions were distributed in the right way for the analyses done, and so on. And that's not, that might seem a bit trivial, things like the statistical package actually carries out the statistics it says it does. But there was a recent case where it was found, I think it was the partial eta squared or something in SPSS was not actually being calculated correctly. So those assumptions, they are real assumptions, even if we regard them as a bit trivial. And incidentally, part of that problem with SPSS, because it's a private company, the software is hidden, can't be publicly checked. And that's why there's new software being developed, JASP, J-A-S-P, which is freeware and free, so that anyone can check the code that goes into it, and that makes you on safer ground in terms of it doing what it says it does. The only other thing I want to say about auxiliaries is just to make sure they're additional assumptions, so they're not part of the substantial theory. So something like subjects will value apologies in imagination. That's not an additional assumption. That's part of what the theory is saying. So the auxiliary hypothesis has to be other things you need to assume for the test to be a test of the substantial theory. I'll go through some examples here. Well, say one example is always that the variables measure and do what they say they measure or do. So that the ratings of how valuable and reconciling the apology is reflects people's actual feelings on the matter. Now, when you assess which is the next question, how safe is that assumption? When you do the assignment, I'm not looking for you to be hypercritical and call everything unsafe. Say I demand more evidence for this, and I'm not looking for you to say everything's safe. I'm just looking for genuine judgment. So in that sense, there isn't a right answer. Just be honest with yourself and say, do you think this is good enough? At least good enough that if you got results opposite to prediction, that would count against the theory in your mind. My personal judgment here is when they took the ratings initially, they all intercorrelated highly. They have plausible face validities, as far as I'm concerned. So I'm happy to treat that as safe. But that's entirely your judgment, as I say. There is the issue, though, that relates to this one of demand characteristics we need to seriously consider. Subjects did not determine the point of the experiment and respond according to demand characteristics. So with ratings, that is an important point. Demand characteristics are a common issue to think about with any psychology experiment. It is mitigated to some extent when you have a between subjects design, because then the subjects don't know what it is they're being compared against. And this was between subjects. So did the subjects really know that this is a comparison between reality and imagination? My personal judgment is, I think it's unlikely that they would have sussed that by being in one of the conditions, and so actually I regard this one, as it happens, as a safe assumption as well. People imagine the apology as having equivalent objective characteristics as the real ones subjects received. So we need to make sure, when we're comparing imagination and reality, that the extent of the authenticity of the apology was the same. Because if subjects imagined, highly normative, they imagine the face of the person really apologizing and meaning it, that might have a different impact than a message on your brief message on your computer screen. And it's not necessarily to do with imagination versus reality. It's to do with what you imagined compared to what was there. Now, what the authors say is they got people to imagine the identical apology. So I think I'm probably okay on that one. They were showing the message and said, imagine this. Well, I think that's what they did. They're not entirely clear. Now, here we come to two very interesting points which will help us think about experimental design and experiments in general, which maybe are not as well understood as they should be. So you might say, don't we assume the subjects in the two groups did not differ systematically in mood, in socialization about the value of apologies and so on, that might affect the outcome of the experiment? Because let's say people in one of the conditions happen to have a more positive mood than the other condition, or happen to be socialized more about the value of apologies in one condition rather than another. And you could go on listing differences between subjects that might be relevant. Did they differ in empathy, in how extroverted they are, and so on and so on. Did they differ in their age? So these sort of participant characteristics that might be relevant to the outcome, there's a large number of them. So shouldn't we be worried about them? Well, Fisher introduced a little piece of magic here that is really, some people regard it as the thing that makes an experiment, and that's random assignment of participants to groups. And the authors said in every experiment in that paper, they said they randomly assigned participants to groups. Now, when you come to do your project or any research, random assignment really means random assignment. So let's say you've got three groups. What you might do is you have three cards labelled 1, 2, and 3. You shuffle them. That's the order in which you're going to assign the next three subjects. You shuffle them again. That's the order in which you're going to assign the next three subjects, and so on. So then you have a genuinely random process by which subjects are allocated to groups, but in a way that assures even numbers in each of the groups. So that's a random process. So that means the only way that one of the groups would get more sad people, more empathic people, and so on than the other is because of the vagaries of chance. But that's exactly what we control for by any statistical method that we use, whether it's p-values or Bayes. So yes, it might happen by chance, but it will happen such that it affects our outcome only 1 in 20 times by chance if we're doing significance testing, and that's exactly the risk we've said in advance we're prepared to take. So in that sense, we've accounted for it by the beauty of random assignment. So 4 is actually safe because they're randomly assigned. Random assignment wouldn't be, by the way, I think this participant is suitable for this group. I think this participant has a good imagination, I put them in the imagination group. Okay. Well, let's say you're doing a mood induction experiment. This person's quite happy, I put them in the happy induction group. That is no longer random assignment, that introduces systematic confounds into your experiment, and you would now no longer know whether it was your intervention or the way or the type of participant that was responsible for any difference between groups, which is why random assignment is so important. And random assignment, maybe it's okay, but random assignment doesn't even mean if you've got two groups, I'll put the first one in group A and the second one in group B, and you do that all the way. Maybe the more extroverted person, they come in pairs, and the more extroverted person is always the one who's a little bit forward, you see. How do you know? So, just to be safe, random assignment, use a genuinely random process like card shuffling, random numbers, flips of coins, to assign your subjects to groups. And it's so important, as I say, that experimentalists regard that as, in some cases, the defining feature of an experiment. Well, now let's move on to another situation in which randomness plays a role. You might say, are the subjects really representative enough of the population to which the theory applies? So that you say, these are just undergraduate students from some university, whereas the theory is meant to apply to, human beings, or human beings who value apologies. So surely this undermines the experiment. Well, here, the role of randomness is slightly different. If you've identified the population to which the theory applies, you would perform random selection from the population. You could do anyway. Then you say what you have is representative of the population because you've randomly selected from the population. So you need to clearly define the population. Now, random selection, again, really means something. It doesn't just mean, oh, I sort of selected arbitrarily from the sort of people we're talking about. So it comes up in voting, if you're trying to predict voting. If you only contact those people who have email to say how you're intending to vote, you now have a biased selection of the population. Because the people who don't have email may well vote in systematically different ways than the people who do. So what you have to do is you have to have a list of everyone in the population, assign them a number, use random numbers to determine which ones you're going to test, and then you've got to work bloody hard to test those people, track them down and test them. That is random selection from population. Psychologists don't do that. Yeah, very important, say, for predicting voting. Psychologists, it's not so important. And the reason why it's not so important is that we only need, for the test to be a test of the theory, we only need to do a population to which the theory is meant to apply. Because if it fails for that population, the theory fails. So we don't need a test of the population, right? We only need to make sure we've identified a population, even if roughly, to which the theory applies. So therefore, a falsifying observation transmits back to falsifying the theory. So what we do is we don't do random selection at all. We just select any way we can. Undergraduates sign up for credits or whatever it is. It's kind of hard to say exactly what the population is. It's something like psychology undergraduates at that university. But in any case, we don't really need to say, as long as we can say the theory applies to these guys. All right? And so the role of randomness is rather different in these two cases. It's crucially important that we randomly assign subjects to groups, and that's easy. But it's not important for the integrity of the test that we randomly select from the population, and that's really kind of convenient because that's difficult. Just put your hands up if you understand that distinction between random assignment and random selection and the role they play in theory testing. Have I been clear on that? Just put your hands up. Excellent. There's a good show of hands. Some of you, perhaps a bit uncertain. Can I get you now to explain it to each other? And then we'll move on. So just to... Okay. So incidentally, I just want to add a sort of a footnote to what I said. It can be a very interesting issue when people try to directly replicate an experiment. So the initial experiment was done in America, they directly replicate in China. You don't get the results. Then it is really interesting to think about, well, maybe there's cross-cultural differences going on here. Maybe it applies to some populations than another. Then you can think about your substantial theory. The fact that it doesn't apply in one of those cases, didn't apply in China, does falsify your theory. Right? So there was a population to which it was meant to apply and it didn't. The theory is false. So now we need to come up with a better theory. Yes?
Doesn't that really limit the scope of psychology theory creation? Because if every theory can only, well, if you resign yourself to the fact that in psychology or another social science you're never going to get a population sample that's going to be representative of more than a select group of people, you can never invent a theory that's going to try to explain the behavior of everyone. And therefore, that just kind of limits the scope of this.
I'll put it the other way around. We try and invent theories that do apply to everyone because we know if it's falsified for any subset of humanity, the theory is falsified as a generality for everybody. And that's precisely why, first we want to come up with a theory that's boldest and most interesting theory we can come up with, so we apply it to everyone. we find a group of people which it doesn't apply, you might just give up on the theory and say this doesn't work for human beings. But if you, as I said, ran it with a distinct group, maybe culturally different or different in age, socioeconomic status or something like that, and it seemed to work in some cases than another, now we're in a position to come up with a more interesting theory, a richer theory that we hope does apply to everyone. So we might say certain people think more holistically, other people think more analytically, as defined by certain practices and upbringing in different cultures, and that explains the differences. But this new theory then is meant to apply to everyone. So you think, aha, what other cultures are like China in training people to think holistically? We'll try it out there. So at every step of the way, we're coming up with theories we hope applies to everyone. At least, that's my recommendation, because you want the boldest, most interesting theories.
Doesn't that just lead you down a road of massively complex? You'll end up with the most complex rule for everyone, which disintegrates into just saying everyone's different. And then you really explain nothing.
Yeah, so there is a danger that, so in other words, the danger you're saying is psychology in the end will destroy itself because there are no regularities about human beings. In the end, there's just individuals behaving individually. I think from what we have from psychology so far has given me sufficient confidence that that isn't where we're going to end up, that there are regularities that apply to human beings. But that is an article of faith, unlike that. Right, so that's the Popper section. So now we move on to orthodoxy. And, well, I say orthodoxy, but I'm trying to get you to do something within the orthodox framework that's a bit better, that's out there, namely think in terms of null regions and intervals instead of significance testing. So the first question was, have the authors determined what minimal difference could be expected if the theory were true? Well, the general answer to that is no, they won't, because it's extremely rare that you see a paper where they've done that. They'll say, if not, determine one yourself and state your reasons. Use to construct a null region. Well, I suppose state your reasons is a bit of a rhetorical question. So I'll deal with study 2 here, which is about someone's cheated on you, they've given you an apology, and then you get a chance to give some money back to them for a second time. And it's 10 euros is involved. So what would be, if there's a difference between reality and imagination, what would be a minimal, meaningful difference? Well, I don't know how to point to something objective about it. There's $1 seems meaningful to me. If there's a $1 difference between conditions, I think that sounds, substantial enough. 50 cents? It's probably. So I had to reach deep in my soul for this one, take a good hard look, and I came up with 20 cents. But I have no justification for that. But you have to do that process. If you're an orthodox statistician, and you're going to use power or confidence intervals to accept null hypotheses. So, if you find this process difficult, part of it is me saying to you, yeah, and if you're going to insist on doing orthodox statistics, this is what you've got to do. And it's difficult, isn't it? It's subjective. It's arbitrary. In a sense, it's not entirely arbitrary. And 20 cents, I'm sort of happy with. Yes, question?
Sorry, I was just going to ask, so minimal difference is not a term of art, I think, for a way to understand this in its ordinary sense.
It's an ordinary term. What it means is, so what I've said, so my null region is from minus 20 cents to plus 20 cents. What I'm saying is differences between groups, and they're minimal in the sense they're so small that, even if God told me this is the real difference in the population, I would say, well, that's so trivial that how could I be interested in that? It's as good as, it's as good as zero, or it has no, it shouldn't bear on our theories, or it doesn't have practical relevance. It's so small as to be irrelevant. So, whether you use it, maybe, sorry, put euros there. That should be cents. Oh no, it is euros. I got it right, didn't I? Because I've 0.2. So I'm just interested, what numbers does anybody want to share their number for a minimal meaningful difference? What did people come up with? Does anybody want to say? Why don't you just discuss what a minimal meaningful amount would be to you for this experiment, and I'll just come around and listen to some numbers. Okay. So some numbers I got, 40 cents, 50 cents, 75 cents. There's no particular reason for these. You just got to ask yourself what would actually be interesting. I mean, if I said to you, if we tested everyone in the world to which the theory is meant to apply, so we have the population, and the difference, when you average over everyone, it's tiny, it's 0.01 of a cent, you would say, forget it. That's not interesting. 0.1 of a cent, probably say, forget it. That's as good as zero as far as I'm concerned. Well, 1 cent. So where do you stop? When does it just start getting interesting? Yes?
I was thinking that minimal meaningful difference between groups depend on the absolute values, especially as the author's papers of behavioural economists. He would have had some understanding of the fact that giving the whole amount, $10, and giving 9 represents quite a big, a different psychological difference in giving, the difference between giving 7 and 8.
Mm-hmm.
You know? And so I don't think that you can just set a minimal meaningful difference, because the difference between like 0 and 1 is different than the difference between say 5 and 6.
Right. So what your argument is saying is this is not a suitable case for parametric statistics and t-tests.
Yeah.
We don't have the right sort of scale. So then, so that gets back to auxiliary assumptions. The results are analysed incorrectly in that case. So let's just, so good point, and you'll be right because of I'm sure you're right about the end effects there. But just so we can carry on and use the analyses as given, we then need to come up with a minimal meaningful amount if we're to assess the sensitivity of the study to enable us to interpret, to say anything about support for a null hypothesis using conventional statistics. I mean, really it's a matter of asking yourself when does it become interesting, because what other basis do you have? Although sometimes, I was asked about looking at other papers, when authors often use 1 to 7 rating scales, and extremely common, if you know about literatures that use 1 to 7 rating scales, you often find a difference between groups of about, say, 1/3 of a rating scale point. Significant, and the author's getting excited by it. Well, what that's telling you is 1/3 of a rating point is taken as real and interesting by that community. So probably a minimal meaningful amount is smaller than that. So you can use previous studies to get an idea of the sorts of things that people are taking as real. But I kind of suspect they didn't pay much attention to the effect size, the raw effect size, and we're just looking at the p-values. And they were just going to get excited if p was less than 0.05, no matter what the effect size. That's my guess. So we have a null region, and then the next question is to calculate a confidence interval and use it in the null region to argue whether or not the data sensitively distinguish the alternative and null hypotheses. Well, you have the mean difference. So I'm doing study 2, 1.89 cents. To get a confidence interval, we need the mean difference. We also need the standard error of the difference, and we can get that if we know the f or the t that they used. The thing what we'd like is the t, and the thing you just need to know is an f done in the same situation as you do a t is really the same test. You just square the t to get the f. So you can square root the f to get the t. They happen to give us f's. You square root it to get the t. So that's just worth remembering. In a situation where you would have done a t-test, the f is just the square of the t. Another thing to remember is that the t depends on the mean difference in the standard error. So if you want to find the standard error, it just is the mean difference divided by the obtained t. The actual mean difference obtained divided by the actual t obtained. That will give you the right standard error of the difference. So any paper worth its salt should give you the mean, so you get a mean difference, and it should give you the f's and the t's, or the t's, so you can get the standard error. Now, the next thing you need to know to do a confidence interval is the critical value of t, the two-tailed. Remember, two-tailed, to get a confidence interval, it's a two-tailed critical value at the 5% level. You need to type in the degrees of freedom, and that will be written in the f, or written after the t. So if they have an f, it will be f brackets 1, 40. 40 is the degrees of freedom. If they have a t, they'll have t, and then in brackets 40. The 40 is the degrees of freedom. So this website asks you for given degrees of freedom, it then gives you the critical value of t. It's going to be around about 2. Right? So you know you've got it right, you've got a value that's close to 2. 2.02 in this case. Then the confidence interval is the mean plus 2 times the standard error, and the mean on the one side, that's that, and on the other side the mean minus 2 times the standard error, and that's that. So the mean plus 2 times the standard error, the mean minus 2 times the standard error. I say 2, I mean precisely this number here. Well, in any case, look through that, make sure you understand it. If you have any questions on the sort of the procedure there, just email me, email Better Study Direct site, so everyone can be clarified. So that's just a little procedure you go through, and you end up with an interval that says it goes from here to here. Why don't you just define a confidence interval to the person next to you before I carry on? Okay, so to clarify one thing, because the interval has 2 ends to it, that's why we're doing a two-tailed critical value, even though we're making a prediction of a directional prediction, right? To get the confidence interval, which goes from one value to another, that has 2 ends, so it's a two-tailed critical value. Now, the confidence interval, everything outside the confidence interval is significantly different from your sample mean difference. You can exclude, what that means is you can exclude, you're allowed to exclude, as possible population differences, you're allowed to reject everything outside of the interval. But what that means is everything within the interval remain as possible population differences. Now, is 0 in that interval? From 0.1 to 3.6. Is 0 in the interval? No, 0 is not in there. Another way of saying that was there was a significant difference from 0. Or people just say it was significant. Okay. But now we're thinking in terms of intervals. We have the null region. And, well, see, it depends what your null region is, but I came up with 20 cents, 0.2. So this confidence interval spans the null region, which I have said the values in there are so small, damned if I'm interested in them, and values outside the null region, which I've said they're sufficiently big, yes, they do count. So what does that mean? So what follows from this? Yes, data insensitive. So what I'm saying, my data are consistent with values I think are so small to be trivial, but it's also consistent with values that are so big as to be interesting. So I haven't distinguished the interesting possibilities. I haven't distinguished the null region boring values from the interesting values. So it's insensitive. So you see, when you think in terms of intervals, you're giving yourself a tougher task than you do just in terms of significance testing. But what do we gain by that? What we gain is the ability to assert null hypotheses, because if the confidence interval had been within the null region, I could have asserted the null region hypothesis, the null hypothesis. If you just do significance testing, you're not in a position to assert a null hypothesis ever. So that's the end of orthodox statistics. We now move on to Lakatos. State the hard core of the research program the authors are working in. So we can go back to this diagram here and put a Lakatosian spin on it. So the hard core is a subset of stuff over here. Theories and ideas that motivated the current substantial theory. It's a very particular part of it. It's those core ideas that have historically persisted for some time and motivated a number of particular substantial theories. Furthermore, ideas that the authors wouldn't give up on just because some particular motivated theory had been falsified. So the particular theories are what Lakatos calls protective belt. So when we were doing Popperian science before, Lakatos would have said, that's all good, but what you're doing there is working in the protective belt. Just remember there's the research program, the whole research program, which includes the hard core, in which you have hypotheses protected from falsification. So that's kind of how it fits in with the Popper notions that we had before. So the hard core isn't something you can logically get at, as someone here was saying before. You said you read up on de Crema and you found he works within a behavioural forecasting paradigm. So he's historically had, and you can get that from the introduction, he's had a certain commitment to a certain set of ideas that have motivated particular papers. So now just have a go saying what you think the hard core is with the person next to you. And again, I just want to say, it's not as if there's the right answer to that, because it's not as if the paper is going to say, and this is my hard core. Okay? So what you want to do is to think of something. Is there something I can say which I think has been there for some time, historically, which I think that has been not directly put up for test, but has been motivating, inspiring particular theories that are put up for test? Okay, so this is what I came to. It's basically the behavioural forecasting type idea. People systematically underestimate the behavioural and emotional reactions in a broad range of domains. Yes?
Sorry, in practice, I understand that Lakatos and Popper have different
Yes.
theories, but in practice, the answer to this question is going to be quite similar to the answer in 3, which is what background knowledge inspired this theory, but it's not being directly tested.
Yes. As I say, it's a sort of a subset. The hardcore is a subset of those things. So certainly in 3, you might have mentioned the hardcore, but you might have mentioned other stuff that wasn't the hardcore. So, yeah, good point. And the other thing this relates to is the substantial theory, because this is fairly close to a substantial theory that was mentioned previously. Well, if it's your substantial, this has actually come up as a mistake in previous assignments. Sometimes people have mentioned as the hardcore the same thing as the substantial theory. But that can't be right. Why can't it be right?
Because the substantial theory of testing that can be falsified by testing.
Exactly. The substantial theory is the thing that you would give up. Right? Whereas the hardcore is something you're not going to give up. Is not going to be falsified. So you think about it in relation to the substantial theory. So if you had the substantial theory, a claim that was similar to this, people systematically underestimate the behavioural and emotional reactions in any domain which they're imagining versus in all domains in which imagination versus reality is going to involve underestimates. If you say for all domains, and that's your substantial theory, which is essentially what we had before, then that cannot be your hardcore. Right? So just be clear about that. Now, I'll put it here in a broad range of domains because that renders it essentially unfalsifiable. So it doesn't apply to topologies. That's all right. It does apply to this, this, and this. Let's carry on using it to think about somewhere else where it might apply, you see? So you can keep it as your guiding idea even though you're not directly testing it yourself, and that's your hardcore. Does the paper contribute to the research program in a progressive or degenerating way? Well, remember, progressive means, theoretically progressive means you make a novel prediction. Do they make a novel prediction? Well, as far as I can tell, they do. They predict that this behavioural forecasting phenomenon applies to apologies. Okay. I'm no expert, but just based on the paper, it seems it's novel. So theoretically progressive. They test it and confirm it. So it's empirically progressive. Okay. So the paper contributes to the research program as we've defined the research program in a progressive way. Yes?
Can you just recap what would be a degenerating way?
Degenerating means they don't actually make a novel prediction.
In the case where it's a replication of a previous paper, is that degenerating?
Yeah, so we discussed that in the Lakatos lecture, but it's a really good point because you think, well, isn't that the case then where it's degenerating? And that sort of depends. If you're taking your replication to be part of, the direct replication to be part of the process by which you're establishing the claim that defines the result that you're replicating, then my answer was you're still contributing in a progressive way, because what you're doing is you're still making sure we can accept the result. Because only when we accept the result, which is itself a sort of a low-level regularity or a hypothesis, it's only when we decide to accept the result that we have confirmation of the prediction or negation of it. But if it was a well-established result that's been replicated many, many times, and for your research program you have it as my prediction of this research program is this result that we already know, then that wouldn't count as a novel prediction. So Lakatos likes predictions to be novel. And we discussed a tweak on that, temporal novelty or use novelty. Yes?
Can it also be true that they can not really make any headway in a particular research program, but there could be other research programs to which this is progressive?
Yes, and that's the really interesting case, where one research is contributing progressively to one, but not to the other, because that's how research programs, despite being unfalsifiable in themselves, can outcompete each other. So that is a really interesting case. Yeah, so back to direct replications, which is of relevance to your assignment. So my answer is a result. When people say I have a result, what they're actually claiming is a hypothesis. For example, they're saying when people they say what I found was that if you prime people with achievement words, then they try harder on crosswords. Well, that's actually a hypothesis, because all you've actually observed is Bill did this, Jane did this, Sarah did this, and so on. But you're not claiming that Bill did this, Sarah did those are particular observations. What you're claiming is when you prime people with achievement words, they try harder on crosswords. So what people say as a result is actually some low-level regularity that probably bears on a substantial theory. So do we accept that regularity? Well, not just with... So the thought is not just with one experiment. We need to directly replicate it. But there comes a time when you've directly replicated enough, you then accept the result as genuine, and then it can count against the theory or for the theory. So to the extent the replication is still in the business of saying, is there really this result there, and making it safe or unsafe, then it's still potentially contributing in a progressive way. Does that make sense? At least that's my take on the situation. Right, final section. Sorry, I didn't give you a break, but I thought if we get through this, you finish early, and then, yes, was there a question?
Oh, yeah, just
Yeah.
a real quick one.
Yeah.
Does it have to be progressive or degenerating? Isn't there a case in which we consider a piece of research just to leave us where we started?
But in a way, that was Feyerabend's criticism of Lakatos. He said, isn't it just all shades of grey, really, and how much progressiveness is really progressing and so on. But yeah, I could see the pattern of research overall, you might say, it's not clearly progressive or degenerating. Although what Lakatos tried to say about that was as long as you do make some novel predictions, and at least some of them are empirically confirmed, then it's progressive. So you can have a fair amount of failed predictions in your predictor belt, because that's what predictor belt hypotheses do. They sometimes fail. All right, the Bayes section. The first two questions are really just asking you to note down again a couple of things you've already worked out, but because they're relevant to the question, let's get them down. So what was the mean difference and what was the standard error of the difference? We worked it out before. So, that question is slightly different, but now the issue here is to, can we come up with, given our theory, an expected size of difference? What I'll do here is, or a maximum, so this is what I'm going through in this slide. Ignore the exact wording of the question there. Now, I'll deal with study 2 because it introduces, it's just slightly more complex. I mean, for study 1, you could use the pilot and just say the difference in the pilot is my expected difference for study 1. Fine. Study 2 follows 2 previous studies and uses a different scale. So just slightly more complicated. So I'll just go through that just to give you some more conceptual tools. So the mean difference in the pilot on the rating scale was 0.75. Now, if you're analysing study 1, you could say, well, that's as good a guess as any, as the order of magnitude I'd expect. That's fine. Now, that could be your expected effect size for study 1. Now, study 1, it was 1.75. So if we're doing study 2, what we could do is find the mean of both studies, 1.25. That's using all the information. But note this is on a 7-point scale, and study 2 is 0 to 10 euros. So I'm going to do something which I think is just a simple way of converting between the two scales. This scale goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got 11 scale points. This was a 1 to 7, 0 to 7 scale, 1 to 7 scale, so it had 7 scale points. So I'll simply scale up by that ratio, 11 to 7. You could do it other ways, but this just strikes me as the simplest way of getting between a difference on the two scales. We don't really know if the scales will behave in the same way, but in the absence of any other information about this, this would be one way of sort of calibrating. And that leads to a difference of 2 euros. Now, this isn't the one right way of doing it. There's a number of approaches you could do. So as long as what you provide is some sort of informed answer, say based on a previous study, and the good thing about replication studies, direct replications, is this is really easy because you have the result from the first study that the authors were excited by, so that's what you expect for the second study, okay? Unless you've got some other reason. But by default, that's what you expect from the second study. Now, what about a maximum? Well, there is a hard maximum. By hard maximum, I hear there couldn't possibly be a difference between conditions of more than 10 euros. That would obtain if in one condition it was 0 euros and the other condition in the population was 10 euros. Everyone did 10 in one case, everyone did 0 in the other. you then get a population mean difference of 10. It just can't be more than that. That is extreme. Okay? So we have a hard maximum here. But note, this maximum is kind of implausible in the sense that what you'd have to have is everyone in the population doing 10 in one condition and everyone in the population doing 0 in the other. That's kind of implausible, right? It does have the advantage of simplicity, though. We can refer to it without looking at data. So this is more informed, and maybe this is more simple. So to go back to the general problem of, the problem here is how do we model the predictions of H1? That's what we need to do a Bayes factor. How do we, by model, represent, how do we represent what our alternative hypothesis is saying, what our theory is saying? How do we represent what it's actually predicting? Well, it's the same problem as how do you derive predictions from a theory we've been talking about. You have a theory. We've been talking about substantial theory to particular predictions, right? We said we need auxiliary assumptions. What do we want about those assumptions? Well, we want them to be informed and simple. And that's just what it is with the Bayes factor, because doing Bayes is doing science. So we want informed and simple auxiliaries that lead us to representing what our theory predicts. So the maximally specified probability distribution for the difference expected by the theory and justify it. So we can come with 2. If we use the maximum here, we could say 0 to 10. I put a uniform on it. This isn't informed by anything in particular, but it's simple. Or, I said the other rule of thumb you use is if you've got an order of magnitude expected value, you do a half normal, and you scale it by having the standard deviation equal to that effect size you think is somewhere in the order of magnitude of what you expect. So what is this saying? Well, it is saying smaller values are more likely than bigger values. I think there's a good reason for thinking that's a good way of approaching this with the reproducibility project. I found when you take 100 studies published in 2008 and try and directly replicate them, effect sizes are overestimated by a factor of about 2 on average. So whatever you think a good effect size is, probably smaller values are more likely than bigger values, and that's what this half normal represents. So what is the Bayes factor in favour of theory of the null hypothesis? I've asked you to put in a screenshot of the Bayes factor calculator so I can see what you're doing. So I put it in here for the half normal. Sorry, I said to justify it. The justification for the maximally vague theory is simplicity. But the justification for this is you've been informed, and it's otherwise simple. I personally think this is the best combination of simplicity and being informed. This one I find a bit implausible, frankly. This one is informed by the actual same studies in that paper by the same authors in the same lab. So this is the one I'd really go for, but I'm just showing you the other case to bring up these issues. You'd only need to do one of them. I'm not asking you to do 2. But I'm doing 2 here just so you see how to think about it. And you see you get different answers. For the vague theory, the uniform, call it vague because the theory is saying, I don't know what it is. It's from anything from the minimum 0 to the maximum of 10. That's the vaguest a theory can be. This theory is a bit more precise. And the vague theory gets less support by Bayes than the precise theory. Bayes punishes you for being vague. So if you can use the literature, past studies, to help inform you about what you really predict, then that's going to be good for you if the predictions come out. And remember, when you do that, you here or otherwise state the reasons, and the reasons are the calculations we did here. The reasons are I based it on the previous 2 studies and then rescaled a little bit. That's how I was informed. And then a reader of your paper or of this is in a position to see whether they buy those reasons. If not, you have an argument about it. Come up with better ones. So do you remember the criteria here? What would follow from this Bayes factor of 2? Yeah, we had our conventions of around about 3 means evidence is worth taking notice of. So this would be saying the evidence isn't particularly strong. It's not really worth taking note of yet for the vague theory. But here, this is above 3, so the evidence is worth taking note of for the more informed theory. And since, for me, in terms of assessing the substantial theory in the paper, I'm going to go with informed theory, this does suffice. This is evidential support, worth taking note of for the substantial theory over the null hypothesis. Screenshot here of what you do. You say, in terms of the distribution of plausibilities of different population values given the theory, it's not a uniform. So then these boxes come up. And for the half normal, you always put 0 here, and you always put 1 here. Then you're left with just one box, and what you put in there is your estimated effect size, the order of magnitude effect you think is going to go in there. Here you put in the mean difference, sample mean difference, and the standard error. Click go, and you get the Bayes factor 5.42 as I've reported. Final question, and we're home and dry. What does this Bayes factor tell you the t-test does not? Well, that's sort of going to depend on what you get and the paper. I've put something here, fairly general. Of course, you can't copy this, just to be clear. You can't just put this as your answer or paraphrase it closely. So now that I've said it, you're going to have to think of a different way of putting it or something else to say. But they both provide support for the theory rather than the null, in that, you know, the t-test was significant and the authors took that as support for the theory. And the Bayes factor tells you their support as well. What a Bayes factor does, by the way, which you don't get from Orthodox, is it tells you the amount of evidence. I know authors sometimes say that they got strong evidence or weak evidence. That isn't a conclusion that follows from orthodoxy. No orthodox statistic tells you that. The Bayes factor is the measure, continuous measure of degrees of evidence. The t-test just allows a black and white decision to accept or reject the null, in this case to reject that. So in one sense, in a pragmatic sense, they came to the same conclusion. And, but if you want to get ideological about it, conceptual, they're radically different things. And in a given situation, they might be very different. So, for example, for a non-significant result, the t-test might not allow any conclusion to follow at all. It's just non-significant. But the Bayes factor might tell you the degree of evidence you have for the null, and it might tell you, actually, there is substantial evidence for the null here, something t-test can't tell you. Or it might just say it's insensitive, and that's something you didn't know from doing just the t-test. All right, so that's everything. I hope that's now helped you sort of integrate and pull together everything we've covered in the course and seen a little bit of the connections and the overview and given you a set of conceptual tools for approaching research generally. Now, when you come to doing your own assignments, please feel free to use Study Direct to ask questions so that everyone benefits from the discussions that we have. Thank you.
Can I ask a question?
Yeah.